Hello, everyone. Uh, let's start today's discussion. Today, we are gonna talk about the JTAG boundary scan standards. JTAG stands for Joint Test Action Group. We are gonna use and talk about the IEEE 1149 Part 1 to define all the aspects of the JTAG testing and boundary scan. Uh, we are gonna see the definition. We are gonna talk about the effects of these JTAGs on the digital system design, and we are going to talk about why actually this standard was developed and how this standard would affect every single digital system that we design or interact with. It's not just a tool for testing. It's basically helps all the manufacturing for also programming or debugging the complex digital systems without having a physical probe and external measurement into that testing configuration. Now, let's start with the context. Basically, from 1970s and 1980s, those decades, the digital logic system start evolving and gets more complex, and that evolvement was very rapid. So all the device that once basically used deep packages and maximum has like 8 to 16 pins, they become more complex. There was like PLCCs and TFPs and eventually VGAs packages adopted to those ICs, and it becomes like all of them would have like hundreds of pins as input and output on their chips. And beside that, the PCB design also went from like a one layer, two layer design to like 4, 6, and even 10 layer design. So all these complexity and density basically happened very rapidly. The upside of this change was that it gives us a better performance, it gives us a density for the design, but there is a trade-off, there's a downside to that complexity, and it was the fact that we lost access to the critical nodes in our system, in our board, so we no longer are able to like have a physical probe to the necessary signal testing. So that loss of access basically ruled out all the traditional test methods, which most of them were based on like a bed of nails fixture, oscilloscopes, or like a logic analyzer. All of them actually needed to directly connect to the PCB traces or the component pins, but and those traditional, when we wanted to like detect the fault on those traditional method, uh, now that there is a complexity and density, we either need to have like an invasive probing, which damage the circuit, or another choice was to have like an expensive X-ray inspection. So uh, that wasn't a very favorable option for industry. JTAG, that IEEE 1149 family, was actually developed and expanded to address this problem. Now, it doesn't happen like in one day or in one round. There is an evolution that happened to the IEEE 1149 family. It started with part one, IEEE 1149 Part 1 at 1993. But the first version was a little ambiguous in a definition and terminology, and it wasn't precisely defined the testing practice and the architecture. So they need to like kind of like revise that. There was an amendment on 1993 to that standard that clarify all those terminology and ambiguity and give us a very solid definition for all the critical components for that boundary scan testing. Now, it's not just the part one. We had several other standards in that family. One is 1149 part 4, which is a mixed signal boundary scan. That standard was developed to basically extend the boundary scan for testing the analog or mixed signal component on the digital ICs. We have the part 6 of 1149, which is a high speed differential interconnect testing, which basically address the problem that the traditional JTAG cannot test the highest speed differential link like LVDS or HDMI. So that part basically was developed to address that problem. And the reason was that all those like highest speed differential interconnect was normally the pattern was AC coupled. So that was a problem with the original JTAG kind of like standard. This part developed to address that. Another standard that is relating to this category is IEEE 1532, which is the in-system programming. That standard was developed for in-system programming of the programmable logic devices, the PLDs or FPGAs. So that standard basically supports full programming flow. It would be the arrays, write, and like security features, like authentication. It covers in the 1532. Oh, sorry. And at the next standard, we had the IEEE 1687, the IJTAG, which is the embedded instrument access, which was developed to access the embedded instrument inside the integrated circuit through a kind of like a reconfigurable scan network. So the difference between the part 1 and part 6 is that the part 1 give us a static kind of like test configuration, test base, but the part 6 will introduce a dynamic kind of like routing for accessing the different instruments based on their configuration. We are going to talk about the 1687, the IEEE 1687 IJTAG in our next discussion on Thursday. So that's one of the most important kind of like standard in the family. But what happened that industry actually adopt this standard, adopt the JTAG inside their manufacturing process. And let's talk about why it's actually considered essential to that. So we had the semiconductor industry, and basically in that right now the JTAG is implemented virtually in a virtually all the modern digital ICs. It's not an option. It's basically now a mandated kind of like part of all those ICs. So all the semiconductor companies embedded that JTAG circuitry in their chips. And right now they rely on the JTAG for both manufacturing test or even runtime debug mechanism. We also saw an interest for the JTAG testing in the board and system level vendors. So it's not just a semiconductor and chip and microprocessor or microcontrollers. Actually, the original equipment manufacturer and original design manufacturers also integrated JTAG into their board level validation and testing. So because basically the JTAG give them the ability to have an automated board level testing configuration. So it allows the boundary scan testing to be performed when we're dealing the system level. So it would also test the interconnection between all the chips and microprocessors also beside the internal inspection that it has in the each individual IC device. But it's not just the manufacturer and vendors. It was very interesting by the compliance bodies, the one that has to like certify all the products. So basically, they adopted JTAG as a reference. So all the regulator and like a organization that publish standards like IEC, IEEE, or GDEC, all of them use that JTAG test configuration as a reference. So they develop all their criteria, all their process based on this architecture and this methodology. And actually it's considered a very essential tool for high reliability system like aerospace, aviation, telecommunication. All those basically rely heavily on the JTAG testing. Now, we already talked about the problem that we had in order, and we developed the IEEE 1149 Part 1 to address that problem. That problem was physical inaccessibility of the complex digital system with multi-layer kind of like board, and we basically embedded a serial scan architecture that gave us the access to all the ports, all the input, output, or bi-directional ports in all the digital chips and ICs, which basically gave us the vendors and all the stakeholders testing platforms and a debugging environment. So they basically convert the external testing protocols, external testing process to basically an automated internal testing ability. Now, we already talked about the boundary scan I mentioned that several times. Let's talk about the definition of the boundary scan. What is the boundary scan architecture? So in boundary scan, we insert a scan register. We call it a boundary scan register, or BSR, between all the input and output pins of the device and its internal core logic. That means that, okay, every pin is dedicated as a scan cell, okay? And these scan cells could act like a digital taps that can intercept or inject logic values, and all of them are connected in series. They are serially connected scan cells to form a shift register. So we are going to talk about that more in upcoming slides, but this architecture, these scan cells are connected, as we said, in series in a chain, and allow us to have a serial access to all the input-output port in our device. So we have both control and observation in all the ports inside our chip. Now, by using this interface, basically, and it basically is an internal scan logic. Basically, we eliminate the need for having an external kind of like testing and observation configuration. All those scan cells that we talk in series, they are going to have like a connection with the outside of the chip to a specific port. We're going to talk about that. One is the TDI, another one is TDO. TDI is the input that we inject the values, the testing data to the chain of the scan cells, and the TDO is the output when we actually observe the result of our testing. So we could have a pattern recognition of seeing if there is a fault, if there is a defect in the system, or even like if there is a defect in a soldering in the board. Okay, so this is very kind of like helpful kind of like a tool and architecture. This architecture, as we said, is basically introduce a non-invasive testing material. The structure supports a functional isolation of the pin. So what that means? That means it allows all the input-output pins behavior to be manipulated, okay, independently uh, from the core logic circuit that we have. Okay, so it gives us the kind of like the system that can operate in synchrony with the test signals and basically give us the ability to have a predictable and synchronized data flow through our system. Now, we talk about the boundary scan cells a little bit in our previous slides. Let's introduce the definition of those basically scan cells. The JTAG testing, everything in JTAG basically rely on how these scan cells operate. So basically, we have some small hardware circuit that are inserted between the device core and all the pins, the input, output, or bidirectional pins. And what it has is the core purpose of that is to capture the signal values, okay, from all the pins or internal logic and inject or overwrite those kind of like signals that going to the pin. So as we said, all the scan cells are connected in series. So it's like head to tail, each scan cells, and each port has their own individual scan cells for the JTAG testing. So, but there is several types of these boundary scan cells, and it depends on the pin that they are kind of like connected to. We have the input cell, which basically connected between the input pins in our chip and the core logic, and basically it captures what it has is inside that input cell is a flip-flop, okay, that samples the logic level on the pin and basically is triggered by the test controller. We call it tap controller. We are going to talk about what is tap controller. Uh, During the test mode, this input cell basically block and override the normal function of the logic. So they block the output of the core logic to the pins, and they run and they apply the test vector that we injected through the TDI that we said, and kind of like observe the system. Now, the output cell, another type of those cells, is basically the same, but it's only applied to the pins that are connected to the outputs of that logic core. So the output cells sit between the output of our logic cores and the pins that are designated for the output. Okay. Same concept going through the output cells, and the bidirectional cells that we mentioned is also it's the same concept. It's kind of like the combination of the input and output. We have some ports in our chips that are used both for input and output. So they are bidirectional. So every cell that sits between the core logic and those bidirectional cells are called bidirectional cells. Now that we know the type of the cells and we know that they are basically connected in series, let's talk about the chain of configuration. How these, when we say these are like a serially designed scan cells, what we mean. Let's see what is actually the scan chain is. Basically, as we said, the scan chain is the serial interconnection of all those boundary scan cells. Okay, so uh, let's think about a shift register. Okay, made up of a 1 bit per input output port. Okay, so uh, the input output or bidirectional pins, all of them has their own scan cell individually. Okay, and they are, as we said, linked head to tail, so they are connected in series. Now, the scan chain allows that serial access, that vector, to be shifted through those series of scan cell. And this shift is bit by bit, step by step, and it's triggered by an internal clock that we are going to also talk about that. So basically, the key element of this configuration is, first of all, the overall configuration that we said they are serially connected. And the full scan pass start with the input, that TDI that we defined, the input of these, the whole JTAG configuration, and the data goes through all the scan cells, and then we observe the output as TDO at the end of our configuration. Now, there are different operational modes when we talk about the boundary scan. And these boundary scan cells actually have a very different behavior during each mode. So let's talk about the 3 modes that these boundary scan can have. The first one is the normal. What is the normal? Normal mode is when we don't intercept with the chip. So the chip works as it should be. So we don't run a test, and all the cells, all the scan cells are bypassed. So they don't interfere with the functional signals that goes through the core logic to the ports and to the pins. Okay, so this is the normal. Now we have the test mode, the second mode, which is when those cells kicks in. So when we have a test mode, those scan cells actually intercept with the input-output signals coming from the core logic. So we have a test vector that is injected from the TDI and gets shifted through all the cells, and basically the output cell can these output cells can override the normal output signals and drive that a specific test pattern to the external nodes. So test mode is normally used during a manufacturing or hardware validation, and basically verify the integrity of logic behavior and interconnection of all the pins. Now, JTAG is not just about debugging and testing. It also, because we have scan cells in every single pins, it also gives us observation capability. So we have another mode, it's observation mode. In these modes, we don't run a test, okay? So we don't intercept with the signals coming from the core logic. The scan cells get tuned to capture those values. So we basically have some kind of a real-time observation over how the core logic behave and what is its performance during the normal operations. Now, I said like some kind of real time because yes, it gives us a observation point. There is a very slight delay. It's a very tiny kind of like time delay, but we can ignore that and said, okay, we have a real time kind of like observation. But if you wanted to like go very precise by the book, it's not real time, but we could kind of like uh, accept that delay and say, okay, this is the real time observation. Now, based on those uh, three modes, that means whenever we trigger each of the modes, the scan cells have different states of action. Okay, so for example, if we have the normal mode, or sorry, the observation mode, okay, uh, the state cells go to the capture state. Okay, so they basically capture the real-time values of the pin or that internal logic. So if we go to the testing mode, the scan cells go to the shift state. Basically, there is a clock that when we enter that testing vector, based on the raising edge of the clock, that testing vector shift bit by bit between all those scan cells that are connected in series, and for each falling edge of that clock, the TDO observe the value of those scan cells. So this is how the shift states actually help us. Like this is the state that help us for the testing mode in the boundary scan cell configuration architecture. Now we have update state, which basically the data shifted into the scan cells is transferred to the output. It has a flip-flop pin at the output, which is updated if the input mode, if in the output mode, and it's from the timing perspective is synchronized with the clock, so we could avoid any meta stability. Now, as we said, those scan cells sits between the core logic and all the pins. So it's kind of like interfacing to the core logic. So that why that matter? So these scan cells is not just for interacting to the pins. It's basically because they are between the pins and internal logic. It gave us a bi-directional kind of like interface, and we have to control it very carefully. Why? Because uh, if we don't have it under control, it could interfere with the normal operation of that core logic, or allow the test data flow without. If we control that, we basically control the test data to flow without corrupting the core logic behavior. And that interface actually, as we said, gave us a non-invasive diagnostic capability when we're talking about the runtime, like the operational mode or the normal mode, or in the test process in the test mode. So there are three key aspects. One is that input isolation. So when we are in a test mode, we basically have we have to have like an input boundary scan cells, and we can isolate that the internal core logic from the external signal, so we don't have non-intended logic behavior in our system. So when the test mode is active, like a multiplexer, disconnect the external pins and basically instead it routes the control scans data internally through the chips. Now we have the output override, which happened during the scan operations. Okay. And basically, the output boundary scan cells can override the kind of like the core generated signals and force the specific values to each output pins. And again, in that mode, the multiplexer chooses the scan pass. Okay, so it allows the scan injected values to be driven uh, into the external pins. Now, another aspect is dynamic switching. What's that about? When we wanted to like switch between the test and functional, okay, basically this dynamic switching handles a control logic that you usually use using a tap control signal to control this transition between the testing mode and the a normal mode or the functional mode. These dynamic behavior basically give us the capability of seamlessly transition between the test mode and normal mode. So we don't have any kind of like interference, and we have a non-disruptive kind of like process. Now, what are the consideration that we have to have when we talk about the design consideration of this cell integration? This IEEE 1149 Part 1 provides that standard for functionality and physical integration, but it's not every kind of like aspect of that JTAG testing. We have some real world kind of like constraint, like timing, layout, and like tooling constraint that we have to pay attention when we wanted to like basically integrate that scan cells into our system. And let's talk about like the first one is the timing constraint. So all the boundary scan logic should be designed so it doesn't violate the setup and hold time requirements of the internal core logic. Okay, so you should pay attention and you should make sure that you isolate the scan logic from the high speed or sensitive clock domains, okay? Especially when the scan enabled signal are asynchronous. Okay, so basically any signal crossing from the scan cells into the core logic or vice versa should be preserved in a clock domain integrity and data stability. So we don't have a mismatch asynchronous kind of like clock between our testing boundary scan configuration and the core logic. Because if we have that, then it would be a kind of like kind of like, how to say, there is gonna be a logic failure, and the data that we capture in the pins are gonna be misleading. It's gonna be a false, a kind of like false detection if they are not kind of like working in the same synchronized manner, the two clock in the system. Now, which basically is the also relate to that next constraint, the clock domain crossing. When we have like a multi-clock systems, individual boundary scan register should be partitioned or gated, so we have a domain specific kind of like constraint. So ensuring a clean clock domain crossing is actually very important and critical if we want to have to like a robust boundary scan in our system. If we have an unmanaged clock domain crossing, it basically leads to the data corruption, to the missed test vectors, or false failures when we are scanning the operations. Now, the modern EDA tools basically are automatically insert the boundary scan cells during the synthesis. So what that means, these tools rely on the BSDL language, the protocol that these boundary scan uses to kind of like have the pattern of the input output so we could analyze the behavior. So this language is actually, is the file and kind of like a library with primitives that is there to generate the scan logic that is consistent with the standard IEEE 1149 Part 1. So, and it's automated. So this automation basically reduces the effort, reduces the human errors, and basically ensures the consistent implementation of these configuration with the standard. So it's very important to keep in mind that these whole boundary scan cells should be automated. So it's not manually handled. Now, the test coverage is another limitation or constraint that we face when we talk about the scan cells, and is basically the effect. It means that the effectiveness of those boundary scan cells is heavily rely on the placement of those scan cells, so we could maximize pin and net observability. Okay, so when we design, we have to make sure that each scan cell provide access to a unique testable point, so we don't have a redundant coverage. Okay, so this is the test coverage that we're talking about. So each scan cell, one individual point of observation. Now, let's go through what we already discussed in this discussion so far. We said that these boundary scan architecture give us a self-diagnosis system. So basically, it transforms chips into an intelligent, testable component. So with the this boundary scan configuration, we can internally control using the tap state machine. You're going to see the configuration in the next slide. Device that can test itself without any external probing and a measurement device attached to that system. This mechanism basically support, as we said, automated testing, real-time diagnosis. Okay, we already talked about that, and it's give us a failure oscillation at the device level. Okay, it also, we said, is at the system level, it could kind of like help us to have basically a virtual probe that could help us to diagnose any defect or any failure in the inner connections between the chips. So we could have an observation not only on each chip through whole the PCB. Okay, it is a programmable, so basically it acts like a programmable data bus, which interface between the ports, the input-output ports, and the device. And this makes the scan path very flexible for test infrastructure and actually can be reused for different scenarios. Okay, so it's a flexible, programmable kind of like testing system through the each individual digital system. And beside that, these architecture actually support the seamless integration of that, kind of like higher level standards. Like when we have the boundary scan cells, is not just for IEEE 1149 part 1. We already said there are some uh, other standards in that family. This architecture can also support those application. So it's not just a one purpose, one tool. It's basically a structural foundation for our system. Now, we said uh, and we talked about the different aspects of that uh, boundary scan control. We mentioned some of the word like a test access port tap signals. We mentioned the tap controller. We mentioned the clock, which we showed with T-say key, the tap clock or test clock. We mentioned the TDI, which is the input of our testing system. We mentioned the TDO, which is the output port of our testing system. Okay, and we also mentioned all the scan cells that sits through the ports and it connected in series uh, inside our chip. Now let's talk about those components. We have 5 type of tap signals. One is the TDI. Come on. One is TDO. Help me. Another one is T-say key. TCK, sorry. And TMS is the next one. Come on. Okay. The fifth one is an optional port, which is the TRST. Now, come on. Why these are important? These pins, okay, are 4 and or 5. This the fifth one is optional. Extra pins that are inserted into the chip. So it's not these 4, 5 pins do not work with the core logic. They are an extra pins connected to those chips, so we have the observation and test ability. Okay, so when you see these pins connected to the to each of the microprocessor that you use, so you can be very kind of like happy about that because it gives you a very good opportunity and access to testing your logic design or even debug or even program your logic design. Now, as we said, the TDI is the input data. So we basically use the TDI pin to insert the test vector or the test signal. That test signal, as you see, get entered here and goes through each individual cell that is sitting between the core logic and the ports, the pins. And it goes in a shift register between all these cells, bit by bit. Now, how it triggered? By this T-say key, by this clock. TCK, sorry. So on the each rising edge of the clock, these signals are going to shift at one cell at a time, okay? And on each falling edge of the clock pulse, okay, the TDO here are gonna capture the value of these scan cells and give us the output. Okay, now, for example, let's say if we have a defect here, which this cell is short-circuited to the ground, okay, what's going to happen? We send several vectors, okay, into that boundary scanned system, okay, and we measure the output. When we measure the output, we see that no matter what is the input, we always capture zero value on this cell. So that means we have a short circuit here to the ground. Or if like these two pins have a soldering defect and they are short circuited to each other, okay, we could easily capture that defect and we say, okay, if no matter what type of pattern of test vector we send, these two are always the same value. Okay, so that means we have a soldering defect short circuiting these two pins each other. So this is kind of like one of the example of what's going to happen. Okay, when we talk about the JTAG testing. Now, imagine that you have these chip and you have another chip here and another chip here, chip 2 and chip 3. If the speed of that work with me. Okay, so all these pins are within the PCB are connected to each other. So on a system level, we can observe the TDO of each of these pins. And if we see any defects, like for example, the first pin of this chip should be connected to the first pin of like this chip. So if we see that during the test, these two chips do not have the same value always, that means this trace has a defect. This is kind of like the example of how this testing work. Okay, so but we have to realize that these modes that we talked about, the normal modes, the testing modes, we said that we have to control the system and we have to have a seamless transition between these modes. Okay, so we would control when is the boundary scan, the JTAG testing configuration is in testing mode. So there is no output of the core logic connected to the port, okay? Or we are in an operational mode when we don't inject any testing and all these scan cells are bypassed. So at each pin, we are seeing the output of the core logic, okay? Or we are in a observation mode, okay? When we capture these cells are not bypassed, but they don't intercept with the signal and just capture the signal for each clock. The TDO would give us the real-time observation of how our core logic works. Okay, so this is kind of like the situation. Now, that state transition and what's happening in the JTAG configuration is controlled by the tap controller. So this tap controller controls the transition between these modes and how these boundary scan chain are going to work. Okay, but what are the input of that tap controller? The first input is the clock. Okay, we said that okay, the tap controller controls the shift register, the process of shifting the test vector one cell at a time to the next one using this clock. And it also controls the TDO using that clock to capture the data. Okay, so one input of the tap controller that controls the whole system of when to shift, when to insert, and when to read the observation, the result is the clock signals. Okay, another one is TMS. That TMS is basically controls that the state of those system. We already talked about the states of those scan cells. We had like the that three states that they could have. So how we chose between those steps, we control that through the pulses that we send through the TMS. Okay, now sometimes we need to reset the system, the tap controller. Okay, now we have two options for resetting the tap controller. We could use TMS by sending five uh, consecutive one signal. So we send 5 bit of one, yeah, 5 bit of one in rows through the TMS. That means reset command for the tap controller. Okay, this is one way. Another way is to use that optional pin that we talked about, the TRST, which is the reset button basically of that tap controller. So instead of sending 5 bits to reset the tap controller, we send one signal through the TRST and reset the whole control system. So this is basically how it works. Now, these tap controllers, as you could see, is also connected through the tap register through the private register to the FPGA fabric. Like for example, this is the FPGA, or to the ARM Cortex of the chip. That means it's not just a testing input. We actually can debug or even program the or chip or IC through the tap controller. They normally don't use that basically because normally they are programmed once at the manufacturing facility, or it's not like a dynamic programming. But if we need to have like a debugging on the programming, or we need to have like a change in the programming or dynamic programming, we could use the tap controller at the TDI to insert the data and again program the whole kind of like system. Now, I wanted to emphasize all these five pins that we have, these four are mandatory. So right now in the manufacturing process, in the design process of these digital signal, when you want to design any of those chips, it's not an option. You have to have these pins and the system of the boundary scan cells, the chain of the scan cells in your system. Not an option, it's mandated. It doesn't matter what type of the chip or digital system you are designing. It could be FPGA, it could be kind of like the PLCCs, it doesn't matter. You have to have these two. The only optional choice that you have is that reset input. So you can have it for easier resetting ability of the tap controller, or you can eliminate it and use that 5 bits equal to one in a row in a TMS to reset the tap controller. So this is basically the whole idea of the how we implement the JTAG testing system. What are the components are, what are the constraint and limitation are, how we have to control that, what are the important nodes, so we could like make sure that it doesn't interfere with the core logic, or the core logic clock and the clock of the tap controller are synchronized with each other, so we don't see any kind of like interfered data in our observation points. Uh, what that means, let me explain that because it's maybe not clear enough. So when we are in observation mode, that means each of these cells capture the state of these core logic output. Okay, now imagine there is a clock that defines these output inside the chip. And there is a clock that orders the TDO to observe the state of that scan cell. Now, if these two are mismatched, or they are not aligned with each other, then basically you read the wrong data at the time. So this is why we mean like the timing constraint is important, and the clock crossing is kind of like the important option of these JTAG testing. Now, this is the discussion that we had today for today. If you have any question, please let me know. Otherwise, thank you for your attention. Yes, Daniel, you have
Riza,
question?
can you hear me?
Yes.
Excellent. Great presentation. This is my first introduction to, there's echo, to JTAG. Questions for